Alright. Hi, I'm JC from Real World. We just launched RLDX-1, which is our first robotics foundation model for Dexterity. Thank you for all being here who actually built RLDX. Before we get into details, David, tell me, why are we so obsessed with hands?
The tasks we care about requires human-level hand capability. When you are pouring coffee, the path gets lighter, so you need to adjust pressure with your full finger grasp. If there are moving objects on conveyor belt, you have to grab in time. When you are replacing a light bulb, you need to rotate it fingers. Logistics, service, manufacturing, a gripper can just pick in place, but these tests need a hand.
But today's VLAs already can fold shirts. Why is the hand so important, Donghyun?
Many people guess that it enhances the model intelligence. Even with the grippers, they expect it will figure out everything. More data, and can up the data model parameters. But there are some tasks remaining challenges. This is not due to a model intelligence. The main challenge is dexterity. So we figure out the necessary of 5 fingers dexterity. We design the part of the system around them. That is RLDX.
I see, but it doesn't seem like the hand is the only problem, Seung-cheol.
Exactly. Beyond just having the hands, existing models still have so many missing pieces. They cannot feel, they cannot remember, and they cannot understand movements. That's why existing models fails on so many tasks.
Yeah, here's the one case. When we pour the coffee pot gets lighter. Visually, almost nothing changes, but RLDX reads torque in real time. It feels the weight shifting and knows exactly when to stop. It gives the model sense of touch.
So RLDX could see and feel. What else, Hyewon?
Motion understanding. Think about a movement on a conveyor belt. An object can move left or right and fast or slow. So you need a temporal context. But the model takes only a single frame and decides what to do. So by the time the hand arrives, the object has already moved.
So RLDX captures motion context between multiple frames, so it knows where things are going, not just where they are.
And then there's memory. Say you need to put exactly 10 apples into a bag you can see inside. The model only sees the current frame, so it has no idea how many are already there. So as our model architecture, we chose MSAT, a multi-stream action transformer, to resolve these problems. And I will talk about it in more detail later.
Wow, thanks for the explanation. What about the data size, Soo-hyuk?
That was another challenge. And in a lab, you can collect demonstrations much more easily. But factory environments are often busy and less organized and full of extra things in the scene. So collecting data in those settings is very hard. The main reason is the environment itself, not the cost.
And even after solving all these problems, still it is not a ready-to-deploy model. The model learns a lot from imitating demonstrations, but it doesn't know how to recover from mistakes or how to make optimal moves toward the goal. This doesn't just happen out of nowhere.
Oh, that's a lot of problems. So how did you design around all of this, Taeyong?
We see challenge as a core constraint. So dexterity, the way we say it, it's just not about the hand. It's the ability to overcome these constraints. So we approached each one directly because each carries a different kind of signal.
And those signals are all completely different. So right away the question is, how do you build a single model that handles all of them together?
Alright, so let's get into this. I want to hear how you actually built each piece. So let's start with the model architecture.
We work on the core model architecture. So the question was, how do we process video, memory, tactile feedback, and even proprioception all together? In real-world manipulation, we can't afford to miss any of them. Yet, most approaches barely handle 1 or 2 modalities in a single stream. But when you try to integrate diverse modalities, all with different structures and temporal resolutions, that just breaks down. Here, we chose MSAT, a multi-stream action transformer, where each modality gets its own dedicated stream and joint self-attention lets them communicate. That's how we process all of them without one drowning out the rest.
The brain is model's eyes and brain. It handles spatial, temporal, and higher action reasoning for action generation. To support temporal reasoning, we train vision encoder to extract motion-specific information, and we train in vision language model to effectively process video for action generation. Furthermore, We utilize data for spatial and high-level action reasoning. Each high-level action grounded into lower-level action. As a result of VRM, this is not only understanding the world, but also understanding how to act.
We also had to bridge the VRM and the head. So the VRM outputs a very long sequence of embeddings, therefore passing all of it to the head makes it really inefficient. Instead, we use a learnable set of queries that could pull out only the information needed for action prediction. That gave the head much more compact input to work with, so we could get high performance while getting the inference much faster with 35% of speed up. And on top of it, we used a memory module to manage the tokens so that we can retain relevant context throughout the rollout.
So that's the architecture. And the next question was data. Robots are still rare, then how do you get enough high-quality manipulation data? That's where our data pipeline comes in.
We worked on building a data pipeline for RLDX. Real robot data from factories are very hard to collect because the robot environments are often busy and less organized than lab settings. Also, getting access to these factories is not just a money problem. Safety rules and access limits and worker schedules. So in our model, we built neural trajectory synthetic data pipeline based on video generative models. We first trained the video model on a small set of real robot demonstrations. Then we generate new videos that are not seen during training but can still happen in the real world, making the dataset about 5 times larger. And these changes include such as different objects on worker surface, and lighting, and backgrounds. And I heard that your approach is a little bit different from mine, so how do you do it?
Oh yeah, we are building RLDX for the dexterous hand, and there's no better teacher for learning dexterity than the human hand. We naturally adjust the grip pressure without thinking, repositioning our fingers mid-task. That's the kind of behavior that robots need to learn. And that data has to come from the real human hand. So we prepared this demo to show that capturing the human hand data has a large potential. The problem is teleoperation can't capture that. Joystick or a puppet arm is too slow, too imprecise, and never feels natural. So we built a data capture pipeline that lets skilled operators demonstrate with their own hands directly. And it's not just about the capability, it's about scale. With our setup, we can collect more than 200 demonstrations in an hour.
So cool. Since our generative models do not have action labels, so we use inverse times models to annotate the actions. This gives us video action pair. As a result, we can create a much broader range of situations than physical data collection alone can cover. However, using these pairs as they are can be risky. We introduce a creation method to filter inconsistent pairs because generative models may produce physically impossible motions or inaccurate action labels. We verify each pair by playing the extracting actions in the simulator and discarding pairs where the replayed motion does not match with generated videos.
And this is how our pipeline works. We track the human hand and object together in 3D, reconstruct the workspace using 3D Gaussian splatting, and then we target the entire trajectory onto a robot hands in simulation. This is how a single human demonstration becomes a useful training data for robots.
With the model and data in place, the final challenge was making work reliably on real tasks.
As our team mentioned before, post-training gives us a capable model. But capable and reliably deployable are different things. Simple imitation learning alone cannot get you there. Fine-grained manipulation is hard and dexterous accuracy is low.
Instead of copying demonstrations, the robot learns what actually helps for the task. It takes an action and sees the result, and finally judges whether there is a progress. The question is how the robot sees the progress. We leverage a VLM's visual knowledge for it. With a bit of post-training on a small set of data, we could make the VLM capable of estimating progress for RL training. There is strict requirement for training real robot with RL, which is sample efficiency. Every physical trial costs our effort and time, which is expensive. So it was natural we maximized the model's learning from its own past experiences. We fully leveraged the benefit of batch on policy data rather than constantly sampling from the model on the fly for every training steps.
Combined with progress-aware RL training, we achieve 3 times faster task completion than imitation learning policy. RL policy results in faster and smoother behavior. From just a few number of demonstrations, the model discovers its own efficient way to solve the task. Demonstrations show what to do. RL defines how to be better from those.
Furthermore, in aspect of the data, the model needs to focus on its failure and learn from them, just like using an incorrect answer notebook when you are studying. The data aggregation algorithm in imitation learning called DAGGER makes it possible. Here's how it works. The post-trained model is deployed on the task. Meanwhile, any suboptimal or failure situations are checked. At the same time, an expert intervenes to correct those situations, and those corrections become new additional dataset. These are aggregated to exist dataset, and we train the model. This feedback loop is repeated, then the performance of our model increases gradually and finally converge. This is how we close the last mile between it kind of works and it actually deployable.
Thanks for sharing all of that. So we started with a question, why hands?
Because the task we focus on demanded pouring the copy and capturing the moving object on the line, assembly with precision. Each one exposes the word, each word becomes a module, and together they become the RLDX, the single model that can see, feel, remember, and adapt.
Dexterity is intelligence, that's RLDX. And we are building the hands let robots work where people work. Let's get back to work.